Yeah, the waiting is the hardest part. Every day you see one more card. You take it on faith, you take it to the heart. The waiting is the hardest part. Yeah, I love Tom Petty. I love my Tom Petty impersonation too. Nothing's quite as fun as a good Tom Petty impersonation, people. Pretty much all you have to do is not pronounce any of your words. That's pretty awesome. So announcements are going on right now. So you may hear the lovely voice of our principal, Mr. Nowak, in the background. I'm also trying to shield myself from the noise by putting myself in the box. And it is very echoey in here, so you're going to hear some weird reverberation in this video. But you're going to deal with it because we're grown-ups, we're mature. Yeah, and it's awesome. So, we're talking about the normal distribution. And if you've ever wondered if you're normal, we're not going to deal with that right now. Normal is subjective. But statistically, normal is not subjective. It's a very specific type of distribution that has the following properties. It is symmetrical, it is bell-shaped, and it is a continuous distribution. That does not mean that all symmetrical distributions are normal. However, normal distributions have these properties. So what we want to do is take a look at... Man, these announcements are annoying because I have a meeting to go to in 10 minutes. I gotta get this video done. Oh my goodness! Things are getting crazy in here. Anyways, remember that a continuous variable means that you need to consider probabilities that are in ranges. So, for example, we have this on the bottom. The probability that x equals a or x equals any variable is 0. Because the probability of randomly selecting someone who is exactly 5 feet tall is 0. They'll be close to 5 feet tall. They'll be within a range that is close to 5 feet tall, but they will not be exactly 5 feet tall. Onward. So generally what we use in stats is the standard normal distribution because, hey, instead of using 10 trillion normal distributions, let's look at just one normal distribution that has a certain property. The standard normal distribution is a density curve, which means it has an area of 1, it's centered at 0, and has a standard deviation of 1. So that's what it looks like. Isn't that pretty awesome? So, in light of that, we want to calculate probabilities of density curves because that's the point of density curves. So, let's suppose that we are looking for the area under a normal curve plus or minus 1 standard deviation from the mean. Well, this is where what we call the empirical rule comes in. The empirical rule is often known as the 68, 95, 99.7 rule, and that's actually how I would like you to remember it, the 68, 95, 99.7 rule. So, plus or minus 1 standard deviation gives us an area or a probability of 68%. That means there's 16% above and 16% below, all adding up to 100%. Isn't that awesome? Now let's look at the 95. So if 68 was plus or minus 1 standard deviation, 95 is plus or minus 2 standard deviations, and the middle chunk of data accounts for 95% of the data instead of 68. That means the upper tail has to be 2.5% and the lower tail has to be 2.5% as well. And you'll notice as you go further and further with standard deviations, you encapsulate much more of the data. So already, plus or minus 2 standard deviations covers 95% of all data in a normal distribution. Onward to 99.7. So, 99.7, you might have guessed, is the middle 3 standard deviations of the data. So that's 99.7% of the data. That's plus or minus 3 standard deviations. That means you've got 0.15% of the data above 3 standard deviations and 0.15% of the data below 3 standard deviations. Let's take a look at an example problem. So, using a standard normal distribution, which, yes, I'm writing out, is a standard normal distribution. Wait for it. Let's find these probabilities. Now, one thing I'm going to make a small edit to here Since it's a normal distribution instead of x, what we want to do is use z's. So let's replace all of these x's with z's. Alright, so ladies and gentlemen, pause your video and try to figure out what the answers to those probabilities are. Give yourself like 5 minutes to figure it out and then resume your video. 'Cause I'm free. Free falling. Yeah, I love me some Tom Petty. I need to get back to listening to Tom Petty more often. Been on a country music kick for a couple years. Now I'm in kind of this weird middle zone of music right now, and it's very strange. Alright, so let's take a look at the probability that z is greater than 0. That's talking about the upper half of the data. Well, that's half the data. So the answer there is 0.5. Yay! Alright, let's take a look at the next one. So we're talking about the probability that -2 is less than z, which is less than 0. That's that chunk of the data. Now notice that is the middle that is the middle 95% of the data, except only half of it. So divide 95% by 2, and we are going to get 0.475. Alright, now this one is super fun. So we want to find the probability that we're between -2 and 1. What I want to do is subtract off the area above and the area below 2 to find those probabilities. So we're going to start with 1 because that's the probability of being under a density curve. And we are going to subtract off 0.16 from the upper tail and subtract off 0.025 from the lower tail. That gives us 0.815. And now if you haven't done the last one, pause your video and answer the probability that z is less than 1. Alright, so that is 1 minus 0.16 because we subtract off the upper tail, and that's 0.84. Alright, just in time for me to go to my meeting and for you to have a great day. Listen to some Tom Petty while you're at it, people. Video over.